This episode, I'm speaking to Dr. William Dunn from University College London about observing the solar system in X-ray and searching for life on the outer planets.
Hi, I'm Dr. William Dunn. I'm an astrophysicist at University College London and the Mullard Space Science Laboratory, and I X-ray planets.
Yes, now that's one of the things we're going to be talking about today, isn't it? X-rays and Xray and Astronomy and observing the universe in X-rays. So I thought it would be worth kicking off the podcast with that notion. Why is it that astronomers observe the universe in X-ray? What do they get from X-ray that they don't get from normal or optical light?
Sure. So X-rays tell you about the most energetic and grandest scales in the universe. So typically X-ray astronomy studies things like black holes and neutron stars and the gas that flows between galaxies and galaxy clusters. So these unimaginably large and unimaginably energetic scales. But we can also use them to study planets. And they tell us lots of interesting things about planets that other wavebands just can't tell us.
So it's almost like they can sort of see what would otherwise be invisible?
Yeah, absolutely. So they tell us about the composition of things. They tell us about plasma, hot gas that flows between things. But yes, you're right. Things that you can't see with your eyes. And things that you can't see in the visible light or the ultraviolet or infrared or radio or all of those other wavebands that give us different clues about the various different processes that govern the universe.
Yeah, I think most of our listeners will probably be aware of, sort of grand scale observatories, perhaps like the Chandra X-ray Observatory that's sort of, it's observing galaxy clusters and things like that in X-ray, but your X-ray observations are a little closer to home, aren't they?
Yeah, exactly. So we take the Chandra X-ray Observatory, for instance, the flagship NASA X-ray Observatory, but rather than pointing it at black holes in the center of galaxies or exploding stars or things called cataclysmic variables, which are neutron stars colliding with other neutron stars or with black holes and things like that. Instead of those things, we point them at planets. So we point them at Jupiter or Saturn or Uranus or Mars or Venus, and we see what's going on at these places that are a little closer to home.
Yeah, and your focus, your focus of your work does focus on the outer planets. I was wondering, why do you focus so much on the gas giants and the ice giants? Why not focus on sort of a planet like Mars, for example, or something? Where did your interest in those outer planets come from?
So X-rays give us this diverse treasure trove of different insights into planetary systems. Maybe I'll split the answer up into two separate sections. So firstly, they tell us about the composition and the formation and the potential for life at some of these places. And they do this because, in fact, back here on Earth, we use X-rays and we use X-ray fluorescence specifically in lots of different everyday processes, from checking how much chlorine or fluorine there is in your toothpaste, and particularly on your food, right? You don't want to be consuming too much of that, to forgeries in art and to check whether the paint in some piece of art from the 1800s or the 1700s is the right composition that it should have been if it was painted at that time, to jewelers who will check whether things are made of gold or silver or platinum. So X-rays uniquely give us these insights into the elemental composition of things. They tell us how much oxygen there is, how much carbon there is, how much iron there is in something. And so for planetary systems, that's really useful, right? You want to know how it formed, what it's made of, and what elements exist there that could potentially support life. And so for planetary studies in the inner solar system, this has been used lots. At Mercury, for instance, we've got Bepi Colombo on its way to Mercury right now, and it's carrying an X-ray instrument that will study the composition of the surface of Mercury. And for the outer planets, I think this is super exciting for things like the moons. So we know that Jupiter has these really exciting moons, places like Europa. And Europa has a surface covered in a thick layer of ice, but below that ice, we think there's a water ocean that spans the entire moon, like a global ocean, with more water in it than is in all of the oceans on Earth. So one of the places, if there is life in our solar system, one of the places it could potentially exist is in some of these oceans on the moons of the outer planets. So places like Europa and Ganymede and Enceladus, all of these exciting icy moons with oceans below the surface. But really, to know what chemistry is available for that life, or potentially even to find the life itself, you need to know what's in that water and what's in the surface, and what could life potentially be thriving off. And so to do that, we need to study the chemical composition of these places. And then to do that, X-rays are a fantastic instrument. They uniquely give us these fingerprint signatures that say, oh, there's this much oxygen here, there's this much potassium, there's this much chlorine. And so in turn, that tells us the nature of the salts in the oceans. Are they kind of like our sodium salts on Earth? Do we have sodium salty oceans on these moons, or are they slightly different oceans? Are they chlorine-based or potassium-based salts? And in turn, that has implications for what sorts of life could exist there. And so I think that's one of the really exciting uses for the X-rays for the outer planets, to study these moons and to work out, well, what are the conditions like there, what chemistry is available there, and could it support life? So I said I'd split this into two. So part one is, how do places form, what are they made of, and could they support life? That I think is a really powerful and valuable use of X-ray astronomy. The second is that you can study this stuff called plasma. So in school, typically, you'll learn about three forms of matter. You'll learn about solid, liquid, and gas. But actually, the most prevalent form of matter, of known matter in the universe, is in the plasma state. And so 99% of the universe is plasma. And so really, if we're going to understand all of these processes that govern the universe and govern this plasma, we need to study the processes and dynamics that are happening in plasma and how they control particles and how particles and energy flows across this plasma. And X-rays are also really good for that. They're good for that in multiple ways. So they let us directly image this plasma. They show us precisely what's going on in it, these regions. They show us both, for instance, these intense regions called radiation belts. So we know that Earth has radiation belts, Jupiter has radiation belts, Saturn has radiation belts, Uranus has radiation belts, Neptune has radiation belts. It seems like it's almost a universal property of magnetized planets that they have these intense regions called radiation belts. So radiation belts can have particles that are up to ultra-relativistic energies. They're crazy energetic, and if you put a human in that environment, it would be really, really bad for them. But we know that the plasma that occupies these regions around planets doesn't start at ultra-relativistic energies. It starts kind of at very tepid and calm energies, EV energies. But somehow processes in plasma physics are able to take particles that are very chilled out and not really doing anything particularly exciting and accelerate them all the way up to these ultra-relativistic energies. And so X-rays let us image these regions and try to work out, well, how is the universe generating these crazy energies and able to accelerate particles to them? They also tell us about the boundaries between different regions. So there's this amazing space mission about to launch in a couple of years' time called SMILE. And SMILE will use X-rays to study the boundary between the Earth and the solar wind, this stream of particles that comes out of the sun. And so it will actually directly image that boundary for the first time. We've never imaged this magnetosphere as a whole, this region around Earth as a whole. It will take us these images of it, and it will show us, well, how do, for instance, giant storms on the sun, how do they impact the whole of Earth's magnetosphere? How do they nudge it? How do they squash it really, really tightly? What processes are happening there? So I think there's this huge array of possible uses for X-ray astronomy for planetary systems, and really it's been underutilized for decades now. And so what I think is really exciting about the coming decades is we're really going to start to utilize it to study the composition, the formation of these bodies, their potential for life, and also fundamental plasma physics that governs the entire universe and how those processes work, and therefore, because we can't visit all of these other places across the cosmos where these processes happen, but we can study them in our own solar system, how the universe as a whole might be behaving and the dynamics that might govern it.
So do you think that X-ray astronomy so far has sort of been looking too far beyond our solar system, and we've sort of neglected to use this this tool to study our own cosmic backyard?
Possibly. I think naturally X-rays give us these amazing insights into these other systems, and uniquely give us insights into active galactic nuclei and these black holes in the center of galaxies and things like that. Yeah, to some extent, I do think it was neglected for solar system studies. There have been some amazing studies within the solar system, but I think largely it has been underutilized as waveband, and there's lots of potential for things that we just can't tell with other wavebands, or for it to complement other wavebands. So, for instance, infrared studies of the moons tell us the molecular composition. They will tell us what molecules exist in the surface of the moons, and therefore what molecules could be in the subsurface ocean. But the problem is that the resolution on those observations is often not good enough to, for instance, distinguish potassium salts from chlorine salts from sodium salts. And this is where X-rays can be hugely valuable and complementary to all the other studies from other wavebands, in that they could tell us precisely, well, there's this much potassium or there's this much chlorine, and therefore the salts that you're looking at are these types of salts.
I think those icy moons with subsurface oceans that you mentioned, like, Europa and Enceladus, I think to the layperson who isn't a planetary scientist, they do still ultimately look like completely barren, inhospitable worlds. But obviously, as a planetary scientist, you don't look at it that way. So I was wanting to gauge your sort of just how interesting do you find these moons, and just how excited are you about exploring them? Do you really think that if there is microbial life in the solar system, that's where we'll find it?
I think David Attenborough says right that life finds a way, and everywhere on Earth that you look at areas of liquid water, we find evidence of life. I think the big question here is there something unique and fundamentally different about Earth, and that enables us to be so privileged that life only formed here? Or is life widespread and prevalent across the universe? And I think the icy moons and Mars as well provide really the cornerstones of understanding, well, how prevalent is life? Do you just need liquid water, the right chemistry, and some source of energy like vents at the bottom of the oceans in order to drive the existence of life and in order for it to form? Or are there other things that we're missing? There's lots of things in the biology, and I'm stepping outside of my comfort zone here, but there's lots of things in the biology that we don't understand, that very first formation of microbial life. Like how did it go from replicating molecules to tiny single cellular beings that replicate themselves? And then beyond that, there's also a huge unknown in that there was this billion-year gap between the existence of single-cell organisms and multi-cell life. And so how does that step also happen? And I don't think we fully understand how that happened here on Earth to begin with, and whether that's a big blocker as well at these other places. So I think it's just as exciting. Finding life and not finding life are just as exciting possibilities. That if we don't find life, it means that there is something fundamentally different about Earth, and that gives us this position of privilege in the universe where we get to exist, where life wasn't able to exist, for instance, on Mars or in the oceans on the icy moons. And I think that's the interesting question here. And so coming back to how hospitable it is, I think on Earth we know of all of these different organisms, these extremophiles, where you look at the most extreme environments on the planet, and you still find that life has found a way to exist in those places. And so we have these very extreme environments at the outer planets, and so possibly life found a way to exist there. I think I should clarify here, though, as well, that I don't mean on the surfaces of the icy moons, and not on the surface of Mars as well. For places like Europa, the environment, it's bathed in this very, very dangerous radiation. It's not possible for life to exist in those conditions. Similarly, for the surface of Mars, it's going to be bathed in ultraviolet radiation that's going to do terrible things to any life that would be present there. But possibly in the subsurface, there might be the potential for things to exist there.
What about sort of looking a bit further out to the ice giants, Uranus and Neptune? I mean, last sort of briefly flown by Voyager 2. Do you think we're overdue missions out to Uranus and Neptune?
Oh, I'm so excited by the NASA Decadal. So the NASA Decadal study, this happens every 10 years, and it lays out the priorities for NASA for the next decade. And the thing that came top this time round was a mission to the ice giants. So when I say the ice giants, I mean Uranus and Neptune. These are these worlds at the frozen frontier where we had these momentary flybys by the Voyager spacecraft, and otherwise we have such limited knowledge of these places, but they're crazy weird places. So Uranus, for instance, it basically rolls through the solar system on its side. It and Neptune both have magnetic fields that are offset from the center of the planet. That's crazy in itself. I don't understand how that happens. And that creates this whole system around them of a magnetosphere, this environment around them that's also offset from the planet's center, tilted at a crazy direction to the planet's rotation, and so the whole thing is just whipping and spiraling through space. And then they have Uranus has this incredible system of moons, and potentially, yes, we just don't know whether they could also have subsurface oceans, right? It seems like from the very primitive studies that we've been able to do with this very, very limited data set from Voyager, that they could potentially have oceans, and there could be a system of 5 moons at Uranus that have oceans below the surface. It's going to be amazing to send a spacecraft to those planets and actually kind of start to probe these worlds. And from a kind of planetary formation or cosmological context, we know from exoplanet studies that ice giants are a really common output from planetary formation. There seems to be lots and lots of ice giants across the universe. And yet the 2 that are in our astronomical backyard, we've barely visited. So I think lots of exciting things to come from the ice giants, and I'm really excited for this dedicated Uranus mission and what it will discover, and all of the ways that it will reframe our understanding of the universe.
Are you excited about the prospect of some of those missions to Uranus and Neptune in terms of the possibility for X-ray imaging and observing, and sort of what you could do with X-ray observations of those planets and their moons? Or do you know whether or not that is actually part of some of the proposed missions? A view to taking good X-ray data out there. So
I think they've not been fully defined yet. So I think an X-ray instrument would be phenomenal on those missions. So earlier I talked about how at Earth, X-ray instruments are going to let us image the magnetopause, this boundary between the Earth's magnetosphere and the solar wind, and that tells us about how different regions interact throughout all of space. One of the fundamental questions for a Uranus or a Neptune mission is, well, how does this crazy tilted magnetosphere that's offset from the center of the system, how is that interacting with the solar wind and the particles around it? And I think an X-ray instrument would be probably the only way to image that magnetosphere and fully understand the global processes that govern that interaction between Uranus's magnetosphere and the solar wind. And again, like we've said for the icy moons of Jupiter or for Saturn, taking X-ray fluorescence images to study the composition of the moons of Uranus and the rings of Uranus and that whole dusty system would be really fundamental to understanding how did those moons form, what are they made of, and potentially if they have subsurface oceans, what is the chemistry that's available for life in those subsurface oceans. So yeah, I think it would be a phenomenal mission to take an X-ray instrument. So actually an X-ray instrument has never visited the outer planets, and this is largely because it's only been in the last decade that we've been able to miniaturize these instruments and harden the detectors so that they could fly to the outer planets and they'd be quite lightweight. So I think the opportunity has really just arisen for this possibility, but it's a really exciting possibility with lots of possible options for new scientific discoveries and to address the fundamental science questions for the ice giants.
I'm just thinking now also about Pluto at New Horizons, and then its Kuiper Belt flyby. If we sent an X-ray observatory out to Uranus and Neptune, would you like to see something like that? Maybe like a flyby of Pluto and another Kuiper Belt object? Would there be sort of benefits in X-ray studies of Kuiper Belt objects, for example?
Yes. So for the ice giants, I think an orbiter is essential. There's so much that we don't know about them. The system's so rich with a ring system with all of these incredible moons. So Neptune has the moon Triton that it captured from the Kuiper Belt, and that seems to have plumes of nitrogen that it throws out into the space environment around Neptune. For those worlds, I think an orbiter is essential and not just a mission that flies past. There's too much we need to know that we wouldn't be able to get to know with a momentary flyby. With the Kuiper Belt, I think X-rays would be really valuable for telling you about the interaction between these places, for instance, Pluto and the solar wind, or Charon and the solar wind, and for telling you about the surface composition and if they did have subsurface oceans, like there's some suggestion that Pluto could have a subsurface ocean, what what is the potential chemistry that's available there as well.
Yeah, it's sort of interesting that so far we've mostly been talking about the search for life, and then we've spoken about the study of magnetospheres. Do those two branches of your study overlap in any way? Can the study of magnetospheres in the outer planets or in the solar system tell us anything about the prospect for finding life in our solar system?
I mean, I think in a broader context, it's essential. It's essential for exoplanet systems because we know that the solar wind, all these particles that stream out of the sun, they can strip atmospheres from planets. We see this happening at Venus and we see it happening at Mars, where they don't have strong internally driven magnetospheres and they don't have a strong magnetic field. They just have kind of leftover crustal magnetic fields. And so they don't have this this force field, this protective bubble around them that protects the atmosphere from the solar wind and all of this atmospheric stripping that the solar wind does. And so we think, for instance, Mars once had a very thick atmosphere and the surface conditions there were very much like Earth. It was about the right temperature and it had liquid water existing on the surface. And we know that then it lost its magnetic field, and at the point where it lost its magnetic field, the solar wind no longer had a barrier that stopped it accessing the atmosphere and stopped it tearing off the atmosphere. And so Mars's atmosphere has gradually been torn away by the solar wind over billions of years now. So from the context of exoplanets and understanding the potential for them to support life, knowing whether there's a magnetosphere there that can protect the atmosphere and can keep a thick and habitable atmosphere there, I think is essential. So the signature of these magnetospheres is typically the northern lights of planets. The northern lights act as this video that shows us whatever's going on in the magnetosphere. And I probably should have mentioned this earlier, but X-rays are also a really good way of studying the northern lights of other planets. They tell us about the flow of particles in those magnetospheres and the fundamental processes that are governing those magnetospheres. And they tell us also that there is a strong magnetic field there that's protecting the atmosphere. So I think in a even broader context, understanding whether magnetospheres exist at planets at all is going to be essential for us pinning down from these thousands and thousands of exoplanets we found, thousands of planets orbiting other stars, to narrow those down to a set of planets that we think could be habitable and are worthy of really detailed observations to study for things like potential biosignatures that indicate that there's life or that there could be potential civilizations on them. But to narrow down from the thousands of exoplanets we found to the handful that we can study in detail, one aspect of that will be knowing, do these places have magnetospheres? Do they have strong magnetic fields that can protect the atmosphere from all of the dangerous stuff that a star can do to a planet's atmosphere?
Awesome. I always think it's really interesting thinking about these planetary missions because they're sort of generations in the planning, aren't they? And they sort of take decades to plan and to actually get going. And that sort of brings us on to one of the things I was going to ask you to tell us about today, which is the Orbits program that you're involved in. I was just wondering if you could tell us a bit about that and how you sort of hope to inspire those sort of future generations of planetary scientists and astronomers.
Yeah, so I think in the UK we have some really chronic issues with science as a whole. We have chronic diversity issues. So, for instance, from sixth form onwards, so after school students are 16, we see this drop from 50% of students being girls to only 20% of students being girls. We also see that you're only a third of students studying A-level physics come from low-income backgrounds, versus, as in, you're 2/3 less likely to study A-level physics if you're from a low-income background than you are if you're from a more well-off background. So and these diversity issues extend to ethnicity, they extend to special educational needs, and so really the problem is that the scientific community doesn't accurately represent the demographics across society, and I think that's a problem that we have to look to try to solve. So we have this array of problems that are systemic problems across UK society in physics. And so Orbits looks to try to address this, and it looks to try to address this by pairing up active scientific researchers with groups of school students for a long-term engagement. So this isn't researchers dropping into the school for a one-off talk and then vanishing and never being seen again. It's them meeting with the school students weekly or fortnightly for up to a year. And they'll work with the school students on a research project. And really that tries to transition so that the school students gain ownership and they gain leadership of that research project, and they decide the direction that it takes. And so what we see from this is we see some of our schools report, for instance, 100% increases in the number of girls taking A-level physics if they do this project at GCSE. We see dramatic increases in the number of students from low-income backgrounds who go on to take A-level physics and go on to do physics at university. I should clarify here, though, that the program isn't about advertising physics. We're not some kind of sales pitch for physics. It's just about making school students who otherwise wouldn't get these opportunities aware that these are pathways that exist and that they could potentially take if they wanted to, and making sure that they're aware that this is something that they can do, and ensuring that we build their confidence both in their ability to see that people like them do these subjects, but also in their ability to see that they can actually do physics. And so they're the goals for Orbits, that we pair researchers with schools, and we do it to try to make sure that science is more equitable and more school students from underrepresented groups get opportunities to see physics and do physics, and maybe potentially see themselves as physicists.
Yeah, it sounds like a bit like a sort of citizen science project. So are the kids actually working on actual data and helping make discoveries?
Oh, absolutely. So in the last 4 years, we've had more than 200 school students become published authors on scientific publications, and these span an array of different research disciplines. In fact, yesterday, one of my colleagues at UCL, Maria, she's been working with Hyams Park School, which is a state school in North London, and they submitted a paper about supernovae. And they've been studying two different supernovae, and they found that they're actually quite different from the archetypal supernova. We've had students at Hammersmith Academy. They discovered that the same molecules that you would drink in coffee, they're born at the same time as stars are born. We have students at some academies in Nottingham who've discovered really weird, strange things about the winds that come from black holes by looking at data from the XMM Newton Space Telescope. We have schools in southwest London who are currently studying comets and have discovered lots of crazy new things about the tails of comets. Students in Newcastle who are looking at solar observations at the moment, and last year they were using artificial intelligence to study the space environment around the Earth, and they discovered something crazy called the tearing instability in the terrestrial magnetosphere. So that's a paper that's currently in submission. Had students work on modeling neutron stars to see how different neutron stars interact. Students have these phenomenal colleagues, Abby Bray and Connie Hoffman, who were working with Newham Collegiate Sixth Form, and there they were looking at orbiting electrons and how different lasers might change the orbits of electrons. So everything from the largest scales imaginable in the universe to the smallest scales. And in fact, I guess what I think is kind of important about this is sometimes it doesn't work, right? Research isn't an ideal kind of conveyor belt to results. So we had a couple schools, London Academy of Excellence and in Stratford and Preston Manor, who actually, they were doing some exoplanet studies with the amazing Fawkes Telescope Network, and with some of my colleagues who work on the Ariel mission. And they were looking at where we expected there to be a planet. And what absolutely ruined their research project is where other people previously had said, oh, we've discovered a planet, it orbits the star this often. They actually just weren't able to find it. And it wasn't that they weren't able to find it because they weren't looking carefully enough, it's because the planet wasn't actually there. So we have this full range of different research topics that different schools do. And I guess the different thing from citizen science is that you pair them with a role model. The thing that we hear from the teachers is that this has an incredibly humanizing impact on the science for them. They get to know this person as a human being. They get to realize, critically, they get to realize that they're not Einsteins, that we as scientists don't have some unattainable innate level of intellect that no one else can hope for. We're humans and we're fallible and we make mistakes. And by having these repeated interventions and repeated meetings with with the researcher, they get to realize that we are fallible, and I think that's really important for shifting the perception of who can be a scientist. I guess I should also shout out my group. So I had some amazing students last year who looked at Jupiter's aurora. They looked at the ultraviolet aurora from Jupiter and also the X-ray aurora from Jupiter, and they discovered lots of crazy things in the northern lights from Jupiter. Particularly, I had a student called Daisy, and she was so hardworking and discovered so many things that I think we're going to be writing multiple papers for the rest of this year about all the crazy things that she found. Another student called Kirill, who maybe we had a big press release last year, some people might have seen it, where we discovered X-rays from Uranus, and he produced some of the images of Uranus with the X-rays overlaid on top of infrared images to indicate to people where we were seeing the X-rays coming from. So all these amazing things that school students can do and can accomplish and can contribute to research. I think often it's their possible contributions are maybe maligned, and what we're finding is actually school students have a lot to offer to humanities knowledge base as a whole, and can discover all of these crazy things that are happening in the universe.
Absolutely. And, I just to come back to sort of what I was saying about, the missions and projects, especially, planetary missions, they take time even just to get going, let alone to actually launch and to arrive at, a planet, as far away as Uranus or Neptune. So it's sort of quite nice to think that maybe some of the students that you've been working with, they might end up, doing their PhDs on, the whatever planetary mission gets to Neptune, or, that'll end up being their career, like they'll spend 20 or 30 years looking through the data, and it all started, with a sort of with a nice citizen science project at school.
I think that's totally true, and in fact, I think if we do discover life elsewhere in the universe, it will be people who are in school right now who will be the ones discovering it, because the way that the technology is developing, it will probably take us 20 years maybe to get to the point where we can actually truly deep dive into whether these places do support life. And I think if there is life in the solar system or beyond the solar system at exoplanets, it will be someone who's in school right now who will be the first human being to ever discover life elsewhere.
Fantastic. That's a nice thought to end on. Just want to say thanks for coming on the podcast and sharing your expertise with us. And hope to speak to you again soon. And good luck with all your future research.
No problem at all, Ian. Thanks so much for having me. It was an honour to be here. Thank you.